Hi everyone! This was initially supposed to be an online lecture, but since this investigation goes through the holidays, and I know a lot of people are away and everything, so this just happened to be the most convenient mode, I guess. Today I'm going to be going through each of the questions and working through each part. Answers may be released at a later date, but please don't just copy off the answers. The purpose of this video is to guide you through the solutions and prepare for the validation. Okay, so let's first start off with question 1. Question 1 consists of several tables where the geometric sequence and common ratio are given, but we are asked to find the difference. So we're just going to do some simple subtraction to find the difference. So you take one term and you subtract the term before it. So let's say for A, 6 minus 3 is 3, 12 minus 6 is 6, so on, just fill them all in. Same thing here, 50 minus 10 is 40, 250 minus 50 is 200, and so on. For part C, you can see that the geometric sequence is decreasing, so the difference would be negative, just to show the decreasing sequence. 20 minus 100 is negative 80, 4 minus 20 is negative 16, so on. Last but not least is part D. It may look a bit confusing at first, but we're basically just doing the same thing that we did in part A, B, and C and applying it to part D to find a generalized formula or pattern. So, firstly, in a geometric sequence, the common ratio is the constant that you multiply each term by to get the term after it. So in this case, the first term is A, the second term is AB, third term is AB squared, and in between each one sort of is you multiply by B to get the next term, right? So in this case, the common difference would just be B. So we're going to write B in all those slots. Okay. This next part is a bit more tricky, but we're going to do the exact same thing that we did for the previous parts to find the difference. So what did we do? We took one term and we subtracted the term before it. So let's do that for this one. So in this square, the first one would be AB subtract A. In the previous tables, we did one term subtract the term before it. So now we're doing the same thing, but with the pro-numerals that we were given. So the next one would be AB squared minus AB. I'm just going to do the same thing for all the rest of them. Okay, so those would be the terms that go in the differences row. But I guess the problem here is that it's very hard to find a relationship between the difference and its corresponding term in the geometric sequence that we're given, right? So we're going to change the form of these expressions through factorization and see what happens. So I'm going to take out b minus 1. As you can see, I'm just factoring out the b minus 1, but changing the form so that we can hopefully find a pattern. Okay, so now I'm starting to see more of a pattern, because for the geometric sequence term A, like the first term, the first difference is A times B minus 1. For the second term of the geometric sequence, AB, it's just AB times B minus 1 for the second term. So I'm going to write those in now that I've identified the relationship between the term and the difference. That's all the table stuff done. Now we're going to move on to question 1b and see if we can explain the pattern that we've identified. Explain how the terms are related to the terms of the sequence. The relationship we sort of identified before was that, for example, if you take the first term of the geometric sequence and multiply it by b minus 1, you get the corresponding term in the differences sort of sequence. This pattern seems to hold as AB is the second term in the geometric sequence, whereas the second term in the differences sort of sequence is AB times B minus 1. So it's just the same thing, but you multiply it by B minus 1. So the question is really asking, how do we explain this in mathematical terms, right? So we're going to say, for every term in the geometric sequence, let's call this term Tn for now. Then the nth difference will equal to Tn times B minus 1. For example, the first term, which is A, would mean that the corresponding first term in the differences sort of sequence would be the same thing but multiplied by B minus 1. And our explanation has generalized it for all n. Moving on to question 1c, state what type of sequence the differences form. Determine both the recursive and explicit rules for the sequence. So just a reminder, we're going to look back up here. The purple highlighted sequence is the one that we're looking at. As you can see, every term is multiplied by b to achieve the next term in the sequence. Hence, we can conclude that this new sequence is a geometric sequence as it has a common ratio between adjacent terms. Just to recap, a recursive formula tells us what a term will be based on the previous term, whereas an explicit formula tells us what a term will be in regards to its order. So let's start with our recursive formula. An equals. So let's take a look back at the purple highlighted sequence that we're looking at. Notice that each term is the same as the term before it, but multiplied by an extra b. So we can write this as an equals b times a minus 1, which is basically saying it's the previous term but multiplied by b. And remember, for a recursive formula, you need to write down what a1 equals. So in this case, it will just be a b minus 1, because that's our first term. Okay, now let's do the explicit formula. It's a little bit trickier, but we can do it. A to the n equals. For each one of these terms, notice that a thing that they have in common is that they have a times b minus 1. All of them have that. The only varying sort of difference that each of them have is that some of them have an extra b to the power of something else, right? Like this one doesn't have, this one has b to the power of 0 because it's 1. And then this one has b to the power of 1, this one has b to the power of 2, this one has b to the power of 3. And let's number them. So this is the first term, this is the second term, third, fourth, right? And notice that the power on the b is always one less than the order that it's in. For example, the first term of the purple highlighted sequence, the first term has b to the power of 0 because 0 is 1 less than 1. And then this one is b to the power of 1, which is 1 less than 2, and so on. So we can now generalize this in our explicit formula. So we're going to do a times b minus 1 because that's the term that we found that's common in all the terms. But the only varying difference is the power that the b is 2, which is going to be n minus 1 because we said it's always 1 less than the order that it's in. Yep, so that's our explicit and recursive rule done. Now we are asked to develop a formula for the sum to n terms for the sequence. Some notes that will probably be in your formula sheet, but you could take note on it, just try and remember it, is that when you have a geometric sequence series, like the sum of a sequence, Sn, the rule is that it will always add up to this, where A is the first term, R is the common ratio, and N is like the number of terms that you're adding up to. So all we have to do to develop the formula is substitute it in. So Sn, I'll use red. Sn, in our case, A is the first term, and our first term is A times B minus 1, multiplied by 1 minus the ratio to the power of n. So our ratio is B to the power of n, over 1 minus the common ratio, which for us is just 1 minus B, because B is the common ratio. And that's actually it. That's the formula. We just have to substitute it into this. So I'm not going to bother looking back, I'll just write it here, but you can sort of look back and confirm for yourself. The sum that we get is correct because it's the same as like when we actually add it up manually on our class pads. So that's good. You can verify that in your own time. Now, moving on to our favorite question, question 2. Evaluate the following terms of the sequence expressing your answers as mixed numerals. So the first one should be quite obvious, it's just 1.5. Now notice that for the next few terms, they are equal to 1 plus 1 over the term before it. So this part is the exact same as this part. So this one would be 1 2/3, because when you do 1 divided by like a fraction, it's equal to just the reciprocal of this fraction, which is just flipping the fraction. And the next one follows the same pattern, happens to be 1 3/5. Now we're told that the next term in the sequence from part A is 1 5/8. And we're asked to like flesh it out basically, like write it like this. So I'm just going to do this because there's nothing much to say. Given that 1 plus 1 on 2 is the second term of the sequence, state a recursive definition for this sequence. Okay, so first we should determine our first term for our recursive definition. Remember the pattern that we identified above, which was every term is the same as 1 plus 1 over the term before it. So if we work backwards from here, then we find that A1 is 1 plus 1, since this is the second term. So that's just 2. Now for the recursive definition, AN equals. How are we going to mathematically explain the pattern that we identified? Every term is going to be equal to 1 plus 1 over the term before it. We're going to call it AN minus 1 because it's the term before AN. And that's it. That's our recursive definition done. Now, in decimal form, the next 3 terms are, well, those. Describe what appears to be happening to the successive terms and explain why this is occurring. Because I need to explain why this is occurring, I'm going to revisit this question after I finish this section, just because it's easier to explain afterwards. Now, to the infinite sequence. It may look a bit scary at first, but this is just a Greek letter, lowercase phi. You don't have to know that, but like. And this could be easily replaced with x, y, any pronumeral, like normal pronumeral that we use in maths. It's just that they happen to pick this because of notation. Basically, the idea of this informative part of the investigation is trying to explain how to simplify this infinite sequence. Because we know that lowercase phi is equal to that infinite sequence 1 plus 1 divided by 1 plus 1 divided by etc. We know that this part underneath is also an infinite sequence of 1 plus 1 over etc, right? So we can replace this red box with phi. And that's what they've done over here. They've replaced that bottom bit with another phi because it's another infinite sequence. It's the same thing. And then they've multiplied both sides by phi to get this new thing. And this is now a quadratic, isn't it? Because you can move it all to one side. So this can be rewritten as phi squared minus phi minus 1 equals 0. We're asked to solve the equation and give our answers as 2/3 alpha and beta, where alpha is larger than beta. Okay, so I'm going to be using the quadratic formula to solve this, just because I find this the easiest method, but you can solve it in any method you like. Phi equals 1 plus or minus root 5 on 2. Show using operations with surds that beta equals 1 minus alpha. So here, let's just reiterate what alpha and beta are from the question above. So alpha is 1 plus root 5 on 2, and beta is 1 minus root 5 on 2. And when we add them together, which is equal to 1. So therefore we can conclude that alpha plus beta equals 1, and therefore beta equals 1 minus alpha. Okay, hopefully that made sense. Hence show that 1 minus alpha equals negative 1 on alpha. From what we did up here, we proved that beta equals 1 minus alpha. Let's call that equation 1. So what we're really trying to show is that beta equals negative 1 on alpha, right? Because we agreed up there that beta is just equal to 1 minus alpha. And another thing that we know is the exact values of both alpha and beta. And turns out when you multiply them together on your class pad, alpha times beta equals negative 1. So we can also use this piece of information. Notice that when you rearrange this equation, you get this. So we can start from that, equals negative 1, and then beta equals negative 1 on alpha, dividing both sides by alpha. And because we agreed up here that beta equals 1 minus alpha, then 1 minus alpha equals negative 1 on alpha. There are probably a lot of different ways that people are attempting this problem, and a few of them probably work, but this is just the one that I found. I quickly added this part in after making the video. This is just an alternative solution to this part 2 problem. This solution was sort of given to me by someone else, and I decided to feature it here because I'm not sure which ones the teachers would prefer, but you guys can look at both of them and judge which one you want to do. So first I'm going to substitute in the exact values that we found for both alpha and beta, because 1 minus alpha equals beta. That's what we proved in the question above. Which gives us 1 minus root 5 on 2 equals negative 2 on 1 plus root 5. Now I'm going to add 2 over 1 plus root 5 onto both sides to get the 0 on one side. Zero equals 1 minus root 5 on 2 plus 2 on 1 plus root 5. And then I'm going to cross multiply to get 1 minus root 5 times 1 plus root 5 plus 4. And because this is a fraction and the fraction equals 0, we can conclude that the numerator equals 0 because it's a fraction. So when you expand out 1 minus root 5 times 1 plus root 5, we get 1 minus 5 because it's difference of squares, and then plus 4, which gives 0 equals 1 minus 5 plus 4, negative 4 plus 4, and that equals 0, which is a true statement, and hence 1 minus alpha equals negative 1 on alpha. Okay, yeah, sorry guys, that working out was horrendous. I've just attached here a neater version of especially the proofs because they need to be ordered and logical to get marks. And I'm worried that the other ones wouldn't be valid, so either just copy this down or write it in your own words. Just make sure it flows, I guess. Okay, now back to the question that we skipped before. Basically what I wrote, the terms are converging at a value called the golden ratio, which is 1.61803339, etc. Because when you type this value of alpha into the class pad, you get 1.61803339, etc., which is a special thing called the golden ratio. So I said that the terms were converging at the golden ratio because as the term as the terms approach infinity, right? Approach the infinite sequence, which is down here, the value of the term will approach that value. Also observe an alternating pattern where the terms are increasing then decreasing then increasing then decreasing. So generally, if we have a term an which is smaller than phi, then an plus 1 will be larger than phi, and we're going to prove this. So let's let any term, it can be any term, be called an, which is larger than phi, which is equal to 1.618, etc. Let's just let a term be larger than phi. And keep in mind that phi equals 1 plus 1 over phi, which we proved before. So that implies that an plus 1 equals 1 plus 1 over an, right? And because we said here that an is larger than phi, that means that that entire thing is smaller than 1 plus 1 over phi. Because if we have 1 over a larger denominator, then the overall value of the fraction is smaller. Hence, the next term will be smaller than phi. An plus 2 is going to be larger than phi again, and the cycle continues, which is the reason for the alternating pattern. Notice that it's not just alternating increasing then decreasing, but also one number will be smaller than phi, the 1.618, etc., and the next one will be larger than phi, and it alternates like that. Once again, I have attached the solution just because my working out was messy. Here you go. We're up to question 3, almost there. Question 3 consists of a few triangles where in every step each of the smaller triangles is divided into 4 more triangles, and it gets like smaller and smaller. There's nothing particularly tricky about this question. It's more just finding a pattern and then writing it. So practicing your recursive and explicit formulas. I'm going to draw a dash in all the working out spaces. Basically on the left hand side, I'm going to be writing like the formula, and on the right hand side, I'm going to write the pattern in like numbers and words. So the right hand side is like more for comprehending. So how many white triangles are there in the nth diagram? As you can see, the pattern goes 1, 3, 9, 27, etc. So I'm just going to write it here. Pattern 1, 3, 9, 27, etc. And it's going up by times 3. On this side, Wn equals. So Wn is defined as the white triangles in diagram N. And as you can see, in diagram 1, there's 3 to the power of 0. In diagram 2, there's 3 to the power of 1, etc. So we can generalize this by saying 3 to the power of n minus 1. Because the order that it's in, like, let's say it's like the third diagram, then there's going to be 3 to the power of 3 minus 2, which is 3 to the power of 2, 9. That's how many white triangles there'll be. Simple enough. Next one, what is the side length of a white triangle? So the pattern here, I'm not going to bother flicking back, but you can look back. It ends up being 1, then a half, then a quarter, then an eighth, etc. So multiply by times a half, right? Because each time it's halving. So we can write this as a half n minus 1. Same idea as last time. And ln is defined by side length of like white in diagram N. Okay. Part C. Part C is very similar. I'm going to be doing the same thing. The pattern for the fraction of the area that's still white in the nth diagram, it goes from 1 to 3 on 4, 9 on 16, 27 on 64. This pattern might be a bit harder to identify, but it's just multiplying each term by 3 on 4 to get the next term. So literally the same thing. 3 on 4 to the power of n minus 1, where an is defined as the area of original triangle that's white. Consider what happens as n approaches infinity. Well, since 3 on 4 is smaller than 1, when you graph this exponential graph, it will be strictly decreasing and approaching 0. Yep, and that's part 3 done. So now we're up to question 4, which is the second last question, so hang in there, guys. A large number of men are trying to form a human pyramid. It doesn't have to be like those perfect triangle sort of pyramids, as long as there's always one more man in the row below than the previous row. So for example, if the top row had 3, then the row below would have to have 4, and then the row below would have to have 5, etc. And it just goes on and on. So the first question, if there was a pyramid with 3 men in the top row and 10 men in the bottom row, how many rows were in the pyramid? So I think the key to this problem is just applying the formulas for arithmetic sequences series, the formulas that you've hopefully learned in class, and getting information out of them, I guess. So for A1, the sequence that we're sort of looking at from top to bottom of the pyramid is just 3, because there's 3 in the top row. Then there's 4 all the way up to 10. So it's just 3, 4, 5, 6 all the way up to 10. And as you can see, this forms an arithmetic sequence where the common difference is 1. So let's apply this formula. An equals a1 plus n minus 1d. Sub in the information that we know. An is the last term, so that would be 10, and a1 is the first term, so that would be 3. Plus n, we're not sure how many rows, that's what we're sort of trying to find out. So we don't know what n is, and we know that d is 1. And if we solve this, it just gives n equals 8. So there are 8 rows in the pyramid. How many men are in the pyramid? So when you think of the number of men in a pyramid, it's basically just taking the sum, right? Like the sum of all the different terms in the arithmetic sequence. So I'm going to be applying this formula. So a1 is the first term and an is the last term. How many men are in the pyramid? We know that n equals 8 from the previous question, so S8 equals 4, because 8 divided by 2 is 4. The first term we know is 3, and the last term we know is 10. And that equals 52. So that's that one done. Given that there are 3 men in the top row, and there are 117 men in the pyramid, how many rows are there? Again, I'm going to be applying like a variation of the formula that I used before. This one you're probably more familiar with, but it's actually the same thing, just like fleshed out. So we know that the sum is 117 from the question. We don't know what n is. We're looking for n because n is the number of rows. We know that the first term is 6 and we're not sure what n is. So you could maybe solve this by hand, but since this is a class pad assumed investigation, I would just recommend for speed purposes, just put it into your class pad and it will give you negative 18 or 13. And you disregard negative, right? Because you can't really have a negative number of rows. So 13 rows. Hopefully that was clear. For C1, we're told that we have 20 men who want to make a pyramid, and it has to have at least 2 rows, and you don't have to have 3 men in the top row necessarily anymore. What is the maximum number of people that you can put on the first row? Following like the rule of every row having to have like a difference of 1 man. Explain your answer. So I'm just going to assume that you have to use all 20 men, but tell me if I'm wrong. But assuming that we did have to use all 20 men, there wasn't really a systematic way that I found other than guess and check. So I'm just going to be explaining the guess and check. Basically, the key to maximizing the people on the first row, because you have to use all 20 men, you should aim to minimize the number of rows that you have. So basically, I just went from 2 rows, like I tried 2 rows, it didn't work. 3 rows, 4 rows, 5 rows. You want to maximize on first row to minimize number of rows. Let's first try 2 rows. That means let's call like the top row A, like it has A men. And then the second row, like the one below, would have A plus 1, right? So in total, there would be 2A plus 1 men total. But assuming we have to use all 20 men, 20 is an even number, and so this isn't possible because 2a plus 1 is going to be odd. Let's try 3 rows. If we have 3 rows, then the total number of men would be 3a plus 3, where a is the number of people in the top row. But 20 isn't divisible by 3 because if it's 3a plus 3, because we're working with positive integers, this one will have to be divisible by 3, but 20 isn't divisible by 3. So that one doesn't really work either. Let's try 4 rows. 4a plus 6. That would be the total number of men. As you can see, 4a would definitely be divisible by 4, but 6 will never be divisible by 4. So therefore, if we have this as the total, then this entire thing will not be divisible by 4. But 20 is divisible by 4, if that makes sense. So if we have to use all 20 men, it's not possible with 4 rows. So I'm going to try 5 rows. 5a plus 10 gives that. So a can equal 2 to get 5 times 4 equals 20. So the maximum number of men in the first row is 2. It's not a very elegant solution, but I couldn't find anything better. And it should be valid because we did explain our answer. Okay, so just in case you don't have to use all 20 men, if you didn't have to use all 20 men, then you could just have 2 rows where one of them is 9 and the other one's 10. So maximum number would be 9. But that's just in case you don't have to use all 20 men. I'm not sure. Someone can confirm that. This next part I found really confusing at first because I didn't know what any of this meant. So that's the first thing I'm going to do, clarify. T1 is the number of men in the top row. That took me so long to find out. I do not know why. Sn is just subbing in T1 into the sum formula, where Sn is 20 because you can make a pyramid with maximum 20 men. Like that's the number of men you sort of have to work with. And when you solve this on your class pad, you're going to get 5.8. So 5.8 is basically the maximum number of rows that you can possibly make with 20 men. But remember, people and rows are counted as positive integers. So we're only working with positive integers. So that's why we have to round it down. So the maximum number of rows that we can make in a pyramid where the top row has to have 1 person and we have maximum 20 men to work with is going to be 5. So we can have maximum 5 rows under these conditions. And now number of arrangements basically means if you have the top row is 1 person, right? Then the next one has to have 2. So we could make a pyramid like this because we have 20 men to work with, but we don't have to use them all. We can have less than 20 men in our pyramid. So we can have 3. We can just use 3 of them. We could just use 6 of them. We don't have to use all 20. We could use 10 of them, etc. So that's why we go 5 minus 1, because the maximum number that we can make is 5 rows, but we can always use less if we wanted to. So that's why there's 4 arrangements, because you can't have 1 row by itself. So you can have 2 rows, you can have 3 rows, you can have 4 rows, and you can have 5 rows. So that's why there's 4 ways that you can make pyramids using maximum 20 men and 1 on the top row. It's a little bit tricky to get to understand at first, but we'll do a few examples and I'll try and explain them more in depth, and then we can just zoom ahead and do the rest. So the next question, let's say 2, right? The top row has to have 2 men. We're going to copy down this formula and subbing in T1, which we sub into A, because that's the first term. And now to find N, what is n? N is the largest number of rows that you can possibly make under the conditions that we are given, which is that the top row has to have 2 and the pyramid has to be made of less than 20 men. And when you solve this on a class pad, sub in this as 20. Sub in Sn as 20 because that's like the maximum number that we can work with. Then it will just give us like 5 point something, I don't know, but it rounded to 5. Hence the number of arrangements is going to be 5 minus 1, which is 4. I'm just going to go through this again just in case you didn't understand what number of arrangements was. Basically, if we have 2 at the top, then we can have 3 at the bottom. And we agreed here that we can have maximum 5 rows. So I'm just going to draw 5 rows right now. So I've drawn this pyramid where the top row has 2 men and we have used up like the maximum number of rows that we can possibly make with 20 men. And this ends up being 20, so that's good. So we've used up all the men, which is allowed. But if we had 2 in the top row and 3 in the next row, that's also allowed. Like that also fulfills the requirements, right? Because we're allowed to have less than 20 and 2 has to be at the top row. So that is also another arrangement that we can make. Adding 4 more men at the bottom also still works, I guess. And we can keep doing that until we reach maximum 5 and then we can't anymore. Because you can have 2 rows, 3 rows, 4 rows, 5 rows, which is like 4 different possibilities. I'm just going to zoom ahead and do them all. And that's basically the end of question 4. Now we can move on to question 5. We are finally up to the last question, which is about placing dots into patterns that form various shapes. The first shape is a triangle. So if you place the dots into triangle forms, you can get the triangular numbers 1, 3, 6, 10, and 15, etc. And it also mentions this is the third diagonal in Pascal's triangle. You can also arrange them into squares, where it makes the square numbers. So the first question is, how can we solve the sequence of square numbers by using the same diagonal of Pascal's triangle? I'm going to quickly do some naming. Let like this one be little t1, little t2, little t3, etc. And let's name these square numbers t1, t2, t3, t4, t5, etc. So the first pattern that I sort of noticed, I think this question is all about just looking for patterns and expressing them in specifically recursive formulas. So the first pattern I would sort of identify is that, let's say you take t2. t2 equals 4. Well, 4 is equal to little t1 plus little t2, right? Because 1 plus 3 is 4. And you can sort of see that it works for everything. So if you have t3, that equals 9, but that's also equal to term 2 and term 3, like the sum of them. So it's sort of equal to its corresponding little t term plus the one before it. So I'm just gonna say this is add corresponding Pascal's. Okay, I'll call it triangular numbers. Number plus the one before it. Write that in full, Anita. And it says give some examples. So for example, T2 equals t little t2 plus little t3, which equals 4. And I guess I can put another example. Maybe write this out in full when you like actually write it into your investigation, just because I'm worried that this is too vague, but it should be okay. As long as you get the idea. In this case, it's 9. Question B is literally using the same notation, same everything, but they want us to write it in like mathematical terms. Write the recursive formula. So if you look at what we did in A, we can generalize this to Tn equals Tn minus 1 plus Tn, right? Because you take the corresponding triangular number and then the previous one, which is n minus 1. So that one's kind of easy. And remember, it's a recursive formula, so we need to state what t1 is and what little t1 is, which is both just 1, because they start at 1. Okay, we're done. Pentagonal numbers. Let's just call them P1, P2, like this, P5, etc. Write a recursive formula of Tn using little tn. Okay, I think they mean P. I think it was like a typo because capital Tn in terms of like the last question was just the squares. So it would be the same answer. But I'm going to assume that they're asking for pentagonal. So there's not really that much to say about this one. It's just like you have to find the pattern or have known it beforehand. So in general, Pn equals little tn plus 2tn minus 1. And to state like the first term, P1 equals 1. P1 equals 1 because of this one. And I'm just going to test out this pattern. Let's take, for example, P3. P3 equals 12, right? Let's see if this like works. So T3 up here is 6. So we're going to put 6. Plus 2 times Tn minus 1, and Tn minus 1 was 3, and that does equal 12. So it works. I think I've tried it on like all of them, so they just happen to work. So that was the identified pattern. Now complete the first 9 rows of Pascal's triangle. Speed run. It's really messy, but just roll with it. These are technically 9 rows. If you really want to do like the next row, that's fine as well. In case you've never had experience with Pascal's triangle, basically you start from 1, like 3 ones at the top. Then to get the next term, you add up the 2 terms above it. So this one, there's like nothing here. So you just put a 1 there. For this middle term, it's going to be 2 because the sum of the 2 terms above it is 2. And then you do the same thing. This one's 3. This one's 3. And this one's 1, etc. And you just keep going like that. What are the 6th and 7th terms in the sequence of pentagonal numbers? I think they just want us to sub it in. So 6. T of 6 is going along this row. 1, 2, 3, 4, 5, 6. So it's going to be 21 plus 2 times 15 equals 51. And the 7th one is going to be 28 plus 2 times the term before, which is 21, equals 70. Yeah, we finished. So sorry I'm not that great at explaining things. Hope that was kind of helpful. And if you have any questions or like if I made a mistake in the video or you have like a new solution, then just DM me, I guess. And thanks for watching.